Hi, and welcome to this third in a series of videos, short videos on second-order systems and the step response of second-order systems. Now, I showed this underdamped second-order step response before, and we talked about various features of it and how they're related to the performance parameters of the system. I'm not going to go over that again, but we're going to look at some other parameters or some other characteristics of this curve that are important. We talked about the overshoot and how that's related actually to zeta of the system and only zeta of the system. But the speed of the system is important to know. Well, I tell you what, before I do that, let me talk about the overshoot itself for a second. Overshoot is important, and it could be that you have to design a system so that it has no overshoot. Now, the reason for that, it depends upon the system, but you could have, for instance, a motion system that was supposed to take a mass. It could be a robotic arm, or it could be anything, some kind of cart that you're moving around, and you're supposed to take it from point A to point B. Now, you have a system that's dynamic enough and doesn't have enough damping in it that when you do put in the command, go from point A to point B, that's a step input, by the way, the system responds, and it responds very aggressively because there's very little damping in it. So you have a large amount of overshoot because of the low level of damping. Well, when you're moving something, especially in a confined space, which you often find in manufacturing environments, it could be that right past point B is some obstacle that you're going to hit if you go too far. So what might happen is that you're limited in your overshoot so that you don't have mechanical interference between something you're moving and some part of the space that's not moving. So it may be that you want to lower your overshooter, that you have you can have 10% overshoot, that's fine, but you can't have 50% overshoot because you might hit something. Now, as we know, that example came from a purely mechanical system, but systems can be of all types. You can have pressure systems, you can have temperature systems, you can have tank systems where the level of the tank is being controlled. Let's take that as an example. So you go from one level to another level. You command the tank to go from one level to another level. Well, it goes beyond that and then it comes back. Well, if the tank's not high enough, then what's going to happen is that the liquid in the tank could overflow the top of the tank. Worse would be, say, a pressure system, and you tell it to go from one pressure to another pressure, and it jumps up and it goes past that pressure that it's aiming for, goes way up above the pressure that can be handled by the vessel that is containing the pressure, so you could actually have an explosion. Temperature, same way. Most temperature systems are first order systems, not second order, but it is possible to have a second order temperature system too. So if you're trying to go from one temperature to another and you had a lot of overshoot, what could happen is you could increase the temperature to a point that you were melting things or damaging something because the temperature got too high. And this often happens with second order systems. You have failures because the people that are designing them design for one temperature and then move it to another temperature, but they fail to recognize that in going from the one temperature to another, or the one pressure to another, or the one location to another, it may actually overshoot beyond what the aim point. And if you haven't designed the system to handle that extra room or pressure or tank height, then you can have a problem. So that's the problem with second order systems design. If you are designing a system that has a second order response, if you only look at the static conditions or the steady state conditions, there may be a period in going from one to another where you actually have an excursion off into a zone that you hadn't designed the system for. All right, so with all that said, there are some time parameters that are important. This is called the peak time. And the peak time Actually, if you look at this, this looks a little bit like the relationship between period and frequency. Okay? The relationship between period and frequency, you'll have the period here, and then there's a 2 pi here, and the omega d. So this period here, this is not a period, it's a peak time. This peak time is the same as the period, except it's half the period. And actually, if we go up and look at the second order response, this is the low point, this is the high point, and this is the low point again. So the period actually would be from here to here, going from one low point to the next low point, or from here to here, going from one high point to the next high point. So going from the low point to the high point is half of a period. And therefore, that relationship that we see, it looks very much like the relationship between period and frequency, except the peak time is half of the period. And if you look at this, you can see that this point right here is halfway between this point here and this point here, because here we have traveled half the oscillation to get back to the corresponding low point. The second, so that's an interesting parameter for a system and really kind of tells how fast it's going to respond. There's another parameter called the settling time. And the settling time, of course, these are just given formulae, although I kind of described where this one comes from. The settling time itself is how long it takes to get from the beginning to the end. Now the end is kind of hard to define because it's still wiggling and the wiggles die out rather slowly. But from a practical engineering standpoint, you want to know once you get into a certain range here at the end and don't go out of it again, that's actually called the settling time. So what you do is you put a band around the final value, and the settling time is defined as the time that it takes to go from the beginning of the step to the point where you enter that band that you defined and you don't come out of it again. Now, of course, that depends upon how big the band is, how big a tolerance you give around here. And that's actually in this formula here. But what's known and used all the time in industry is you have a settling time that is related to a 5% band. So when you go within 5% of the final value and you don't come back out of it again, that's this settling time. And then you have a 2% band. So the 5% band, it's 3 over zeta times omega n. The 2% settling time, so you're within a 2% of the final value. And once you arrive at that point, you never come out of that again. And that's 4 over zeta omega n. Different industries will have different standards. What I'm going to use always, just to be consistent, is I'll use this 2% band here. Okay, now if we do know the transfer function of the system, which means that we know k and omega, zeta and omega n, we can actually write the equation for the oscillation of the system. And I call this xt, which is a measurement of this vertical value here. Notice that we have an amplitude here, and this will depend upon the size. Actually, what this is the size of the step times the steady state gain. Okay, and then it has an oscillatory component. This is where your oscillation comes from, this sine function here. Notice that the frequency of the sine function is omega d. But then there's this other factor here that has zeta and omega n in it. And this determines, notice that as t goes to infinity, this factor right here is going to go to 0. So the oscillations will die out eventually. you will it won't oscillate anymore. Okay. All right. Now a couple of other things, small points here. Whether the system is overdamped, I tell you what, I'm going to stop here and start it back up again because there's enough left here that it's worth having the time to do a full video.